Hello everyone and welcome to the Academy class. In this particular session, we will take a look into the anode rays or also called as the canal rays. Now, in order to understand this, it was the experiment which was conducted by Goldstone. He performed the same experiment as which was being conducted by J.J. Thomson for his cathode ray experiment. Hence, he took into consideration of a discharge tube. So in a discharge tube, there was certain modification which were been made. For example, the cathode which was been used in this particular experiment, what he did was he perforated these particular cathodes. That means if these are the cathodes, what we are taking into consideration, these cathodes are going to have a small number, small holes over here, something like these. Okay, now these are nothing more than holes which are there in the cathode now. Now, on the second hand, what he did was he took a particular gas in the discharge tube at a lower pressure. So here, what he has taken is he has inserted certain gas. Okay, so and the cathodes what we had were perforated. So therefore, these are the perforated cathodes. And the final modification which was been done is that this particular wall, the wall at the cathode side was having a zinc sulfide screen. So therefore, here was a zinc sulfide screen which was inserted. Now, when a high amount of electricity, a high voltage of electricity was supplied, what happened was it was seen that some rays were being emitted from the surrounding of the anode. Okay, I'm not saying that the rays are coming out of the anode, rather the thing is there were certain rays and these particular rays were coming near the anode, something like these. Okay, now these particular rays used to pass through the perforations in a sense, the holes. When they used to pass through these perforations, they used to strike the particular zinc sulfide screen what we have over here. Okay, as a result of which these particular thing started emitting green color fluorescence over here. Okay, so therefore here the fluorescence also took place. The fluorescence used to take place when the rays that used to come and strike the wall just behind the cathode. Okay, so these rays are called as anode rays because they are getting emitted from the region nearby the anode. Okay, now the important thing that we need to note down is that these particular rays are not emitted from the anode. They are not emitted from the anode, but these particular rays are produced in the environment, or you can say as these particular rays are produced in the space between the cathode and anode. That means whatever the gases that we have taken over here, because of the ionization of these particular gases, these rays were produced, and these rays used to travel all the way to the cathode, but the cathode is perforated. There are holes in it, as a result of which they used to pass through the cathodes and they used to strike with the wall which was coated with the zinc sulfide. And when it used to strike to that particular wall, then what used to happen is there was certain type of fluorescence, a green color glow which was observed. Okay, so this was all about the anode rays. As they are passing through those particular holes, we also call them as the canal rays. Okay, now let's observe what are its important characters. So the first character that what we'll understand over here in this entire aspect is that if you observe, all these particular rays travel in a straight line. Okay, so therefore they travel in a straight line. The second point that you have to understand is that if we are going to keep any particular photographic plates in this particular region, okay, all these particular photographic plates were affected by these rays. So it has a tendency to affect, okay, it is going to affect the photographic plates. The third point that we need to understand is that these positive type of rays, all these rays are deflected if we are going to have any electric or magnetic field over here. Okay, so if we are going to have any electric field, or if we are going to manage to have a magnetic field around the discharge tube, then what we observe is that these particular rays used to get deviated. Now, this deviation is to prove that these rays, what we are speaking, are positively charged. Okay, so the deviation shows, it proves that these rays are positively charged. Now, moving further to the point number 4 is that if we are going to keep any particular thin sheet of metal, these rays have a tendency even to penetrate through these thin type of metal. Okay, but however, the penetration power, okay, the penetration power is less than that of the cathode rays. Okay, now final thing is that these particular rays, of course, as we have already spoken about fluorescence, these rays can also induce phosphorescence. Okay, it is going to induce phosphorescence as well as fluorescence, right? So these are all the points what we need to understand. Let's observe all of these one by one now. So therefore, the first point is that the anode rays travel in a straight line. Second one, as I said, if we are going to place any photographic films, all these particular photographic films of plates are going to be affected. The third point is that the anode rays are deflected under the presence of the electric and magnetic fields. Their deviations, their direction of the deviation proves that these particular rays are positively charged. Next point says that the anode rays can also penetrate through the thin sheet of metal. But the penetration power, this is very important, the penetration power is less than that of the cathode rays, right? Now, the next one is that the anode rays produces the fluorescence as well as the phosphorescence. There are a few more points which I would like to include now here. Now, as we already know that these particular anode rays are positively charged. These are positively charged. Right? Now, here the important fact is that the E bar M, now E bar M is again specific charge. The specific charge, okay, that is the specific charge of these particular rays. Okay, of the anode rays, we will say over here, of the anode rays. What is going to happen is it depends, these particular specific charges, they depend upon what gas we take into the discharge tube. You can go on changing the gas that is present in the discharge tube. Okay, so it is not universal. Okay, so therefore it depends upon nature of gas that has been taken into the discharge tube. Okay, now as a result of which we can say that these particular E by M are not universal, right? Therefore, we can say that these are not universal. Now, the maximum E by M. Okay, the E by M, this particular value is maximum when the gas that has been taken into the discharge tube is going to be the high rotation. Right? So let's observe all these particular points again. So anyways, coming forward with the next part of it, we can say that the protons are the fundamental particles and is a very essential constituent of all the matter. Okay, of course, the credit for the discovery goes to Goldstone. There are a few more important points that we need to know. As we were speaking about the E by M, that is a specific charge. The specific charge was discovered again by Thomson's and Wien. Okay, now they estimated what is exactly the amount of E by M for this particular proton, and they got the value as, they calculated the value as 9.578 into 10 raised to 4. It is going to be the coulomb per gram. Okay, now this was what they had given us, that is the value of E by M of a proton, right? Now, further, we can calculate the mass of proton. Okay, so instead of directly entering to the mass of the proton, we already know that the number of the electrons and the number of protons are equal, and therefore the charge which is present on the proton is also the same in terms of the magnitude, and therefore they determined the mass of the proton, and that was equal to 1.672 into 10 raised to minus 27 in terms of kgs. Okay, so in terms of kg, or we can also say that it is 1.672 into 10 raised to minus 24 grams. Okay, now speaking about the molar mass, again gram molar mass, right? So therefore, molar mass is equal to the mass of proton. What is the mass of proton that we have? 1.6, okay, 72 into 10 raised to minus 24 in terms of gram, because we are speaking about over here as the gram molecular mass, right? So therefore, we are taking over here in form of grams, so therefore I'm choosing this particular value here into Avogadro's number, that is 6.023 into 10 raised to 23, that what we have. So that is equal to approximately, we will get it as 1.008. This is an approximate figure. All right, so there are certain more important points that we need to discuss. We shall do it soon. So the proton bears 1 unit positive charge. Thomson and Wien estimated the value of E by M, and that was found to be as 9.578 into 10 raised to 4 coulomb per gram for a positively charged particle proton, right? So the next point is the amount of positive charge that is present on a proton. Again, as I said, it is same in magnitude as 1.602 into 10 raised to minus 19 coulomb. In terms of ESU, again 4.8 into 10 raised to minus 10 ESU. Right? So coming forward with the next one. And the next point that we need to discuss now here is that the protons. Okay, these protons are present in the nucleus of an atom. These are present in the nucleus of an atom. Secondly, the number of protons are equal to the number of electrons. All right. Now, the next point that we need to understand over here is that in the case of plutonium, ordinary hydrogen. Okay, so in the case of plutonium, okay, in the case of plutonium, what happens here is that the proton itself is going to act as the nucleus. Okay, so itself acts as the nucleus, because in the case of proton, what happens, in the case of an hydrogen, what happens over here is that the nucleus itself is made up of only one proton. Okay, it has only one proton over there. So there are one proton, and of course there is going to be one electron in the case of hydrogen. Right? So therefore, the proton itself is acting as the nucleus in the case of hydrogen atom. Now, if we take this particular hydrogen atom and if we ionize this, okay, so when we ionize this, what is going to happen is that this particular hydrogen is going to lose, it is going to lose the electron. The electron is going to move away, correct? After that only we are going to call it as an ionized hydrogen. So therefore, now there is no electron and only there is the presence of the proton over here. So electron has left out. And this particular condition, this is nothing more than H plus protonium. Okay, so therefore, or we can call it as just as a proton. So proton is nothing more than an ionized hydrogen. Okay, thus the proton is obtained when the only electron that is present in the hydrogen is removed, as the hydrogen consists only of the one electron and one proton, right? So let's observe all these particular points one by one. So first one, the mass of the proton, as we have already seen in the previous case, and that was 1.008. How did we get that? We have got that particular thing by multiplying the mass of the proton along with the Avogadro's number. So this is a gram molecular mass over here, right? Second point is that the proton is present in the nucleus of an atom. The number of electron is equal to the number of proton in the neutral atom. The atomic number of an atom is equal to the number of protons present in the nucleus of that atom. So when we try to define the atomic number is nothing more than the number of the proton which are present in the nucleus of that particular atom. Okay, so next one is the proton is the nucleus of the plutonium. That is a common hydrogen, as we have already explained that. The proton is nothing more than the ionized hydrogen atom, right? So the proton is obtained when only one electron, which is present in the hydrogen, that has been removed. Okay, and the hydrogen atom now, as we already know, because it consists only of one electron and one proton. So therefore, when you remove that one electron out, what you have now is just a simple proton in the nucleus. So therefore, this was all about it. Thank you for watching. To take care.